Hello everyone, once again welcome to ashatech.com. In this video we are going to discuss how to design a binary counter that repeats its count every 5 counts. And now in this video we are going to use a D-flip-flop. If you don't understand what a flip-flop means, I'm going to share a link to the video that talks about those things. But now to just make a recap, to understand a flip-flop, we need to understand what a latch means. A latch is a logic circuit that maintains a given logic condition until changed by an external source. And a latch has got two inputs, that is a set and reset, and two outputs, that is, for example, a Q and a Q inverse. Now, these latches form a basic fundamental building block of what we call storage devices. Those are memory devices because it is from these latches that we are able to build, for example, counters, we are able to build registers, and of course, later on we shall advance from a latch to a flip-flop. So now what is a flip-flop? A flip-flop is actually that latch that has a clock as an input. So in other words, a latch is you will find that the differences between a flip-flop and a latch is that a latch is asynchronous, then a flip-flop is synchronous. Another thing is that a latch does not have a clock input, whereas a flip-flop has a clock input. So let's dive right away to answer this particular problem. One, we are looking at designing a binary counter that repeats its count every 5 counts. Let us take a basic count from, for example, 0, 1, 2, 3, 4. We want a counter that will start from 0, goes to 1, 2, 3, to 4, and then it goes back to 0. So these are the 5 counts. 1, 2, 3, 1, 2, 3, 4, 5. These are the 5 counts. So once it finishes the 5 counts, it goes back to 0. So those are about 5 steps. Okay. So if we look at the values from 0 to 4, these are easily represented by 3 bits. So we are going to use a deep flip-flop that uses 3 bits, and it is a synchronous up counter. In other words, it is going to be counting from 0, 1 to, in other words, incrementing the count by 1. If it was a down counter, then it will be, for example, starting from 4 going back to 0. It would be decrementing. And if it is a synchronous up counter, also it means it is going to be using a rising edge trigger mechanism. And being synchronous, obviously for a flip-flop to be synchronous, it has what? It has a clock signal. So we will look finally at what a D flip-flop means. A D flip-flop has a single data input, which we are calling D, and then we are also saying the operation of a D flip-flop. We are saying it captures the value of the D input at the rising or falling edge of the clock signal and holds this value until the next clock edge. So we said since these form the basic foundation of memory, and we will see that this comes from them being multivibrators. So they are multivibrators. In other words, they vibrate from 0 to 1, 0 to 1, but they are bistable. Bistable meaning that, for example, a flip-flop has 2 stable states. So these 2 stable states is logic 0, logic 1. It can stay in 0, for example, until changed by another external source, or until changed by another triggering mechanism, for example, by using a clock signal. So until you change the state or until you apply an external source, it will remain in logic 0. Now, when you apply an external source, it will again go to logic 1, and in that logic 1, it will be stable. So that's why we call it a bistable multivibrator, because it is stable in two states. In logic 0, it is stable. In logic 1, it is stable. I'm saying it can move from 1, it goes to 0, it goes to 1, it goes to 0. So you find you have 1, you have 0 here. So that becomes a bistable multivibrator. And an example, we are using a flip-flop. So the characteristic equation is that we have the Q as an output. And if we look at the output, for example, this is the next stage. In other words, we have Q, for example, of T, that is the current or the present state, and then Q, T plus 1 becomes the next state. And for a D flip-flop, the input to D to determine the output always depends on the next state, which is 2 t plus 1. So that means every other time you have, for example, 2 t plus 1 equal to 0, also the input to D is going to be 0. If you have 2 t plus 1 equal to 1, then the input to D is always going to be 1. So the functionality is that it directly transfers the input to the output on the clock edge. So we are saying if we have 3 bits, we are going to let them represent which output, Q2, Q1, Q0. We are meaning if, for example, the counter is starting from 0 going to 4, then it will be 0, 0, 0, then 0, 0, 1, 0, 1, 0. So this is 0, this is 1, this is 2, and so on and so forth. So to deal with this problem, we need to also understand what the state diagram is. The state diagram is going to be showing you how those bits are being changed as we count from one state to the other. So we shall be counting from 0, 0, and we go to 0, 0, 1. Okay, then we go to 0, 1, 0. Then we go to 0, 1, 1. This is 3. Then from there we go to 1, 0, 0, which is 4. Then we go back to 0. So this is a 3-bit synchronous counter. So that is the state diagram. It is just showing you how we are transitioning from one state to the other. In other words, from one count to the other. So another thing that we need is the excitation table. The excitation table is going to tell you what is happening on the present state and what is happening on the next state and what is going to be the input to D of the flip-flop. So if, for example, we have the current state being low and we want the next state to be low, obviously, what we are going to put to D is going to be low, because we say this D depends on the next state. State. So if we have, for example, the next state being 1, then our D, that the input to D is going to be 1. If the input, if the next state is 0, the input to D is 0. If the next state is 1, then the input to D is 1. So that is the excitation table, and you have to understand that. So we go to another step, which is now looking at the state table. The state table is also going to tell us how we are transitioning from one state to the next state and looking at what are the inputs to the button or to the pin D of the flip-flop. So we are looking at the present state, next state, and the flip-flop inputs. So if we have the present state as 0, 0, 0, then our next input obviously is going to be, we remember we are transitioning from 0 and we are going to 1. So our next state is going to be 0, 0, 1. So if here the present state is 0, 0, 1, our next state obviously is going to be transitioning to state number 2. So that means our next state is 0, 1, 0. So what is now the value of these inputs at the flip-flop? So D2, we said these D values depend on the status of the next state. So here we see that D2 is going to be depending on true 2, D1 is going to be depending on true 1, D naught is going to be depending on true naught, but of course the next states of the choose. So this one obviously is 0, this is 0, this is 1. This one is 0, this is 1, and this is 0. So the rest you can fill up by following that mechanism. For example, if the current state or present state is 0, 1, 0, you'll see that the next state is supposed to be going to 3. This is 2, so we are supposed to be transitioning to 2. And we are from 2, we are supposed to be transitioning to 3. So you see from 2, we go to 3, and the bit or the binary bit for 3 is 0, 1, 1 if we are using 3 bits. From 0, 1, 1, we go to 1, 0, 0, which is 4. And from 4, we shall obviously go to 0, 0 because we are counting from 0, going to 4, and going back to 0. So that is the state table. Let's now look at the K-maps. So K-maps are going to help us generate the values that we are going to input at, for example, D2, D1, and D0. So let us look at D2. D2 only has a 1 at where? At the value of true 1, true 2, true 1, true 0. So let us look at what is that value is 0, 1, 1. So if we are drawing our K-map, we are beginning with true 2, then true 1, true 0. So here is 0, 0, 0, 1, 1, 1, 1, 0. Then we have 0, we have 1. So we have seen that that D2 here, for example, is having a 1 at 0, 1, 1. So we go to 0, 1, 1, and we put our 1. So what would be now the value of D2? D2 will therefore equal to what? This is going to be 2, 2 inverse, then 2, 1, 2, 0. So that is the value that we are going to input at D2. Then we go to K-map for D1. Also, we have 2, 2 as the most significant bit. Then we have 2, 1, 2, 0. We have 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. So let us check on value for where do we have 1 on D1. So we have 1 on D1 as 0 at 0, 0, 1. We go to 0, 0, 1, and we plot that. Then we go back and look at this other one is 0, 1, 0. So we have 0, 1, 0. So what would be the value for D1? Our D1 obviously would be, let's look at this is true to inverse. Then we add what is the other one? What has changed here? Okay, we have 2, 2. So what has changed here? 0, 1. So, okay. Oh, so this one, we cannot do the looping. So what we do, we write them the way they are. So this is going to be 2, 2 inverse, then 2, 1 inverse, then 2 not, plus, obviously this also becomes 2, 2 inverse, then 2, 1, then 2 not inverse. So this becomes 2, 2 inverse into, this becomes 2, 1 inverse 2 not plus 2, 1 2 not inverse. So what does this mean? This means 2, 2 inverse into 2, 1 XOR 2 not. So our D1 is equal to 2, 2 times 2, 1 XOR 2 not. So we proceed to D not. So let us look at where do we have 1 at D not. We have 1 at 0, 0, 0. So this one, let's feed it. We have 2, 2. We have 2, 1, 2 not, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. So we are saying we have a 1 here. And then finally, we also have a 1 on 0, 1, 0. So 0, 1, 0, we have there a 1. So for this, we are going to do the looping. You can loop this and that, and then we will have our D note equal to this 2 not 2, 2, it is 2, 2 inverse is remaining. Then here, what is changing is 2, 1. So 2, 1 is not going to affect our results since still, even if it changes, it still maintains the same state. So that means we are going to find out that it is 2 not that actually is going to affect our results. So this output is going to be depending on 2, 2 inverse and 2 not inverse. So for that matter, we go ahead on our logic. So when we look at D2 requires, this D2 requires a 3 input AND gate. Then D1 requires 2 input AND gate and an XOR gate. Then D note is going to require just 1, 2 input AND gate. So generally, I'm going to be having how many AND gates? I will have 2 AND gates and 1 XOR gate, then plus a 1. Actually, there are 3 AND gates, but 2 are dual, then 1 is 3 input AND gate, then we shall also have an XOR gate. So let's go to D2. We go to D2. So this is actually, this is not, this is 1, and this is 2. So what does that mean? This is going to be 2, 2. This is going to be 2, 1. So this is 2, 2. This is 2, 1. And this is 2 not. So this is 2 not. Okay. And this is obviously D not. This is D1. And the other one is going to be D2. So when we go to D2, we first go to D2. D2 requires a 3 input AND gate. So we are going to come here. So one AND gate, I mean this AND gate has 3 inputs, and one of the inputs is 2, 2 inverse. So we have 2, 2 inverse. So what is going to happen? We are going to pick a different color, put it there, and let's see another one. Another one is another input is 2 not and 2, 1. So we are going to go to 2, 1. we are going to go to, let's call this chew note, let's call this chew 1. So we are going to go to this chew note, pick an input, we go to chew 1, we also pick an input. So this means this one obviously is feeding this one. Okay, so we move. Then we have two inverse, then XOR. This is chew 1 XOR chew naught. So we go to D1. At D1 we have an AND gate. Okay, we have an AND gate, but when you look at this, one input of the AND gate is coming from chew2 node, and another input is coming from the output of this XOR gate. So what we do, we draw another what? Another gate, which is XOR. So this XOR feeds this. So we are saying that from the chew inverse, chew2 inverse, from this chew2 inverse, we are going to pick a wire and take that as an input D1. Then we need it also pick from chew1, chew1 and chew2. I mean chew1 and chew naught are going to be now inputs to the XOR gate, so that now all this becomes an input to D1. So the inputs at D1 are also done. Then we go to D note. D note has the chew2 inverse and chew naught inverse. So this chew naught inverse is an input to actually an AND gate, which AND gate supplies D naught, and also we are seeing that we need a chew2 inverse. So our chew2 inverse again is available here, so we can take it there and becomes an input. So what is remaining is actually connecting our clock signal. So I'm going to use this color to represent our clock signal. So since this is a synchronous, we are going to give it a simultaneous clock signal. So from the source directly to each flip-flop. So this is a clock signal, and we are taking it to the ground. The rest of set and reset, leave them the way they are. So when you run this, for example, in a simulator, or you assemble it in for example, a lab, these outputs that we are seeing here should be able to give you the output that we are looking at. So you can maybe use a 7 segment, or you use LEDs to show you this kind of output. So you can have your, for example, 7 segment, maybe you use a DCD hex. So you can take those signals, you take your chew2, your chew1, your chew naught. So if, for example, your chew naught is 0, 1, 0, this your chew2 is this is chew2, this is chew1, this is chew naught. This will display a 2. If it is 1, 0, 0, this will display a 4, and it will reset back to 0, 0. So thank you so much for following up. This is how we can design a D flip-flop that can count from 0 to 4. Those are 5 states or 5 counts, and then resets back to 0. If there are any questions as regards to this, kindly please put them in the comment section, And also remember to like, share, and subscribe to enable us serve you better. Thank you so much.